feel free to jump in whenever you have any questions. Like this is a small group. It's like can be totally informal, and feel free to just jump in. So I guess you guys have heard, I guess probably everyone has heard that deep learning is this revolutionary new technology. And some of my favorite examples are self-driving cars. You can watch videos on YouTube of Tesla's like full self-driving beta. And it's pretty impressive. You know, it's not human level yet, but it's way better than it was 10 years ago. Like if you go back and watch videos of self-driving cars from like 2009, they're like so bad. They've come so far. And here, like, it's impressive just to see what the visual system for the full self-driving software is able to recognize. Like it recognizes all these other cars. It recognizes the stoplights. It recognizes the lanes on the road. That's really hard. And like 10 years ago, we were nowhere near being able to do this. And another really cool application of deep learning recently has been, have you guys heard about AlphaFold? It solves or it's at least represents major progress on the protein folding problem. And like, who knows what the protein folding problem is? A protein is a sequence of amino acids. And the question is, if you know that sequence, can you predict the 3D shape that the protein is going to fold into? And if you could do that, it would be very helpful, like in drug design and medicine and stuff. So they have used deep learning to make like major progress on this problem. And a cool thing about deep learning is that it's like surprisingly accessible. Like you can learn how to start doing deep learning without too much math background. And we've had students here at USF who have started doing some deep learning projects even during like their third year. And so part of my reason for this tutorial is I just want to see if we can get some more students excited about learning how to do deep learning. And another reason for this tutorial is that how many of you guys have heard of this website called Kaggle? Kaggle is a website where they have like machine learning contests. And if you win them, if you amazingly win a competition, you can get like $100,000 or like $60,000. But even if you don't win, if you get in the top like 10%, you can get a bronze medal, and that's really good. That's like something you can show on your resume and stuff. You can like talk about that in a job interview. Be like, yeah, I got a bronze medal in this Kaggle competition. And these Kaggle competitions are really fun. They're like very fun. So the purpose for one of the purposes of this tutorial is to try to get some students excited about doing these Kaggle competitions. By the way, Kaggle has a bunch of courses. I haven't tried these courses myself. Chris, have you tried some of these?
I took a peek in the intermediate and the intro to machine learning. They're really good.
Okay,
Insightful.
they're really good. Okay, yeah. I haven't tried them, but they look like they would be good. And it's a good selection of topics. We've got SQL, advanced SQL, deep learning, data cleaning. This sounds like good stuff. These are some of my favorite books about machine learning. I think this book, Hands-on Machine Learning, gives a very sort of friendly introduction, and it sort of walks you through the process of doing machine learning. This book is good because it covers a lot of material in just 100 pages. And this book, Deep Learning with Python, is actually one of my favorite books about machine learning. The author, Cholet, is the creator of Keras, which is part of TensorFlow. And TensorFlow is the deep learning framework from Google. This guy, Cholet, is one of the best deep learning engineers in the world. And he also just happens to be a really good writer. And he explains things in a very simple, clear way. So I recommend that book. And another resource is that we have some GPU. Part of the challenge of doing deep learning is that you need like GPU access to like train your neural network efficiently. And we have some of them. This student, Rock Gu, I don't know if any of you met him. He graduated like a year ago. He actually donated like $10,000 worth of GPUs, and we have some really nice like NVIDIA GPUs. So if anyone wants to access these, just send me an email and I can help get you set up. With this tutorial today, I'm gonna try to tell you like some of the main ideas of deep learning and of machine learning and of deep learning. And I'm going to try to give you like the real ideas that you need to understand how to do deep learning. But there's a danger with this type of presentation, which is that it might be overwhelming, because I'm going to drop a bunch of stuff on you like real fast. And it's kind of like if you're learning to speak a foreign language like French, and someone teaches you like 10 new words all at once, and then they try to have a conversation with you using these words. It's like, hang on a second here. It's going to take me some time to like internalize these words, you know? Try not to feel overwhelmed and don't feel discouraged if this seems like a lot of material all at once. Okay, so I'm going to talk about two fundamental types of machine learning problems. The first type is called regression, and in regression, you're predicting a numeric value. And a classic example of regression is predicting the selling price of a house. Another example of regression is like given an image, predicting the location of various key points in the image. So here on the left with predicting the selling price of a house, there's one number we want to predict. With this image on the right, we have like a dozen key points. Each key point is determined by two numbers, the X and Y coordinates. So that's like 24 numbers that we want to predict. And I'm going to use this example of predicting the selling price of a house as my main example for a regression. The other fundamental type of machine learning problem I'm going to talk about is a classification problem. And this is where we want to predict which category something belongs to. And within the realm of classification problems, there's two types. Well, there's at least two types. There's binary classification, which is where there are only two possible categories. And then there's multi-class classification, where you could have many categories. So I'm going to start by talking about regression. And I'm going to tell you guys, I'm going to try to tell you guys like a recipe for solving these types of machine learning problems, a recipe for solving regression and classification problems. And I'm going to tell you like the ingredients of that recipe. And by the way, all of the ingredients are going to be written in orange. So how do we possibly, let's say we want to create an algorithm that's able to predict the selling price of a house. How do we possibly do that? Well, the first thing we need to do is collect training data. That means we need training data. What that means is we need to go out into the world and we need to look at like 10,000 different houses. And for each of those 10,000 different houses, we're going to record some data about each house. We're going to write down a list of numbers that describes each of the houses. And the numbers that we write down in this list could be things like, the number of square feet in the house, the number of bedrooms in the house, the distance of the house from downtown. This list of numbers, an ordered list of numbers in math is called a vector. In machine learning, this ordered list of numbers is called a feature vector. And these numbers, the individual numbers in the list are called features. Okay. Also, for each of the houses that we look at, we also need to record the selling price of the house. And so here, Y1 is the selling price of the first house, Y2 is the selling price of the second house, and so on. These selling prices are the target values that we want to be able to predict. Okay, so we've got our training data. What next? Now we need a function. We need a prediction function. This is going to be a function that takes as input a feature vector that describes a house and returns as output a prediction for the selling price of the house. And hopefully it will make accurate predictions. And now here already we come up with one of the main questions in machine learning. And the question is, what form should we assume for the prediction function f? What form should we assume? And the simplest thing you might do, or at least a very simple thing that you can do, is you can have f just compute a weighted combination of the features that appear in this feature vector xi. That's like, this is one of the simplest types of functions. And this type of function is called a linear function. So we could choose f, our prediction function f, to be a linear function. Actually, technically, if you've taken linear algebra, then technically this type of function is called an affine function. Because there's this beta 0 term here, this function is technically only linear if beta 0 is equal to 0. But so I'm going to try to call this an affine function, but a lot of times I speak loosely and just call it a linear function. But keep in mind that this, assuming this form for the prediction function, that is only one possible choice. And there are many, there's a whole world of other possible choices. We could get very creative about the form that we assume for this prediction function. We could take f to be some nonlinear function. It could be something called a tree function. It could be a neural network. And if f is a neural network, then we are doing deep learning. Okay. So we've got our prediction function. The next thing we need is we need a way of measuring how closely our predicted selling price agrees with the ground truth selling price of the house. And the way we're going to quantify that is we're going to just compute the difference between the ground truth selling price and the predicted selling price, and we're going to square it. And what do we hope? We hope that this number is small. Because if we hope our prediction is accurate, and if our prediction is accurate, then our predicted selling price is going to be close to the ground truth selling price. That means this number is going to be small. So this function L, which computes the difference between the predicted selling price and the ground truth selling price and squares it. This function is called the squared error loss function. And this is the loss function that we typically use when we're doing regression. This is the most popular loss function for regression. It's not the only possible choice. We could instead just compute the absolute value of y minus y hat. We could just compute the absolute value of the difference between the ground truth price and the predicted price. That would be another option, but this is the most popular option. And this is when you're designing a machine learning algorithm, this is one of the big questions you have to answer. Which loss function should I use? Should I use the squared error loss function? Should I use the absolute error loss function? Should I use some other loss function? This is one of the main questions that we are faced with. Okay, now already we have arrived at a slide that is potentially quite overwhelming. So let's try to parse what we're saying on this slide. And by the way, before I say that, let me go back to our prediction function. Let's say that we're going to use this particular prediction function, which just computes a weighted combination of the features in our feature vector. In this weighted combination, we have these coefficients, beta 0, beta 1, beta 2, ... Those coefficients you can think of as being like knobs. They're like knobs that you can tune. And our goal is to somehow tune those knobs. If we can do a good job of tuning these knobs, then we're going to get a good prediction function that makes good predictions. And so our whole job in machine learning is to somehow tune these knobs. Somehow we have to pick good values for these coefficients that appear in our prediction function. How do we do that? How do we possibly make a good choice for these coefficients? Well, and keep in mind, what are we hoping for? We're hoping that our predicted selling price for the house agrees closely with the ground truth selling price for the house. That's what we hope. We hope that this number is small. And we hope that this number is small for all of the examples in our training data set. For all 10,000 houses. We hope we get a good prediction for all 10,000 houses. Another way to say that is, imagine we compute the average loss function value for all 10,000 houses in our training data set. That's what we're doing here. This is the average squared error. In fact, this quantity that we're computing, this is called the mean squared error. It's the average of all those squared error values. We hope this is small. And if we do a good job of choosing these parameters, these coefficients that appear in our prediction function, if we do a good job of choosing these parameters, then this quantity, this average error, is going to be as small as possible. And so that actually gives us a way to choose the values of these parameters. We should actually select these parameters in order to make this mean squared error as small as possible. This function, capital L, this is called the objective function. Sometimes it's called the cost function. We want to choose this parameter vector beta, this list of coefficients, in order to make this objective function value as small as possible. In other words, we want to tune these knobs to make this objective function value as small as possible. Let's say we've done this. Let's say that we have solved this optimization problem and we have found our vector beta that makes this mean squared error as small as we can make it. What do we do then? How do we actually make predictions? So then we have got our prediction function and we're ready to go out into the world with our prediction function. And somebody might walk up to us on the street and say, hey, can you predict the selling price of my house? And I'll say, okay, give me the feature vector that describes your house. And they'll say, okay, well, my house has so-and-so square feet. It has so-and-so many bedrooms. It has such and such distance from downtown. They'll tell me the whole feature vector that describes their house. And I'm going to take their feature vector and plug it into my prediction function. And then my prediction function is going to give me a predicted selling price for the house. And that's what I do. That's how I use this prediction function. So at this slide, I'm afraid that at this slide, it might already become like sort of overwhelming. Like I'm dropping a lot of stuff on you quickly, because to try to parse this equation, there's a lot of stuff you have to remember already. You have to remember, what is xi? Okay, xi is the feature vector that describes the ith house in our training data set. What is f? Well, f is our prediction function. What is yi? You have to remember yi is the ground truth selling price for the ith house in our training data set. And then what is L? L is our squared error loss function. So there's a lot to parse here. Any questions before we move on? And what I've described here so far, this is how regression works. Like this, a lot of machine learning problems are regression problems, and this is the framework. This is how it works. So what you have to do is choose your prediction function and choose your loss function, and then solve this optimization problem. And then you have trained your model. This, by the way, this prediction function is sometimes called a model. And the tuning these parameters, tuning these knobs, that's called training your model. And this prediction function could be a neural network. So, and then you're doing deep learning. So when you're doing deep learning, you're doing this, and you just have F as a neural network, at least for a regression problem. And by the way, I have not yet said how we would actually find a vector, and it's not obvious at all. How would we actually find a parameter vector that minimizes the mean squared error? That's not obvious. And we'll talk about that more in the future. But to give you an idea of how it might work, in calculus, you learn how to minimize a function in calculus. And how do you do it in calculus? You set the derivative equal to 0, right? Well, we can do something like that in this situation too, something along those lines. We can somehow try to find a point for which the derivative of this objective function L is equal to 0. Okay, so now I'm going to talk about, that was regression. Now I'm going to talk about binary classification. And my example for binary classification is I'm going to talk about predicting whether or not a house will sell within 3 months. So how are we going to possibly create an algorithm that can predict whether or not your house is going to sell within 3 months? So as before, the first thing we need to do is collect training data. So we go out into the world, we look at 10,000 different houses or 100,000 different houses. For each house, we write down a feature vector, a list of numbers that describes the house. And we also write down a label. And the label is going to be either 0 or 1. And 0 means the house did not sell within 3 months. 1 means the house did sell within 3 months. So in binary classification, the target values are just, they're either 0 or 1. Okay. Now, as before, we need a prediction function. Now that we're doing binary classification, our prediction function is going to work a little bit differently. What we want our prediction function to do is we want it to take a feature vector describing a house as input, and we want the output of the prediction function to be a probability. And it's gonna, that probability, we're gonna think of it as the probability that this house is going to sell within 3 months. So if the output of our prediction function is like 0.9, we're gonna say, okay, I predict there's a 90% probability that your house will sell within 3 months. Okay. So now again, we're faced with this fundamental question in machine learning. What form should we assume for the prediction function? And as before, we might consider trying to take f to be a linear function like this, or an affine function. This function just computes a weighted combination of the features that make up this feature vector. Does anyone have any idea what would be wrong with this prediction function? There's something wrong with this.
Like, since you mentioned that it was like 0.9, so I'm assuming it's got to be like on a 100 or 100% scale, and I feel like if we add all those numbers up, it would go over that 100%, and like it
Exactly.
wouldn't give us an exact probability.
Yeah, exactly. The thing is that a probability is a number between 0 and 1. And there's no reason to expect this number to be between 0 and 1. It might be negative, it might be greater than 1. So that is a problem with this prediction function. So we need to somehow modify this prediction function in order to guarantee that the output is between 0 and 1. So the way we're going to do that is we're still going to compute this weighted combination of the features. But then we're going to take that number and we're going to plug it into this function that's called the sigmoid function. And here's a graph of the sigmoid function. This is the formula for the sigmoid function. Here's a graph of the sigmoid function. You can see the output of the sigmoid function is always in between 0 and 1. So this sigmoid function is useful in machine learning because it converts a real number into a probability. That's why the sigmoid function is useful in machine learning. It's used to guarantee that the output of our prediction function is a probability. In other words, is between 0 and 1. Now this formula, e to the u over 1 plus e to the u, that formula looks a little strange. And it's like, where does this weird looking formula come from? But if you were to sit down and try to come up with your own function that does this job for us, that does the job of converting a real number into a probability, I don't think you could come up with a function which is much simpler than this, at least not a smooth function. This is about as simple as it gets for doing that job. There's also something beautiful, kind of beautiful or elegant about this function. For one thing, the exponential function is involved, and the exponential function is like the most important function in math, or it's one of the most elegant functions in math. So whenever the exponential function is involved, like, you know, that's a good sign. what is God's favorite function? It's the exponential function. And also, if you take the derivative of sigma, the derivative of sigma turns out to be something very nice. It's sigma prime is equal to sigma times 1 minus sigma. That's another elegant thing about this sigmoid function. Okay. So if you use this particular prediction function, then your classification algorithm is called logistic regression. Logistic regression is the most fundamental, I would call it the most fundamental classification algorithm in machine learning. And logistic regression specifically uses this particular prediction function. But as I mentioned before, you don't have to use this prediction function. You can get very creative with your prediction function. You could take F to be a neural network. And actually, a whole lot of the most interesting research in machine learning from the past however many years, 10 years, 5 years, has been just getting very creative about the prediction function. Another way to say it is that people, people talk about coming up with different architectures for neural networks. But what that means, they're just talking about the prediction function. They're just getting creative with what they use for their prediction function. By the way, this term, logistic regression, is kind of a confusing term because we're not doing regression. We're doing classification. I think a better name might be like logistic classification. And where does the word logistic come from? This function, the sigmoid function, is it's also called the logistic function for some reason. Okay, so we have our prediction function. What do we need next? We need a way to compare how well our predicted probability agrees with the ground truth label. And remember, the ground truth labels, they're all either 0 or 1. You can think of the ground truth label for a house as being a probability that reflects certainty about the outcome for that house. So if the label is 1, you can think of that as a probability that reflects certainty that the house sold within 3 months. If the label is 0, that's a probability that reflects certainty the house did not sell within 3 months. What we need next is a way to measure how well our predicted probability agrees with this ground truth probability, either 0 or 1. And this is kind of a deep question, like a deep mathematical question. What is a natural way to compare the agreement between two probabilities? What is a mathematically natural or a mathematically beautiful way to compare, to measure, or to quantify how well our predicted probability agrees with the ground truth probability? That's a deep question. You could try computing the squared error, but this is somehow not the most natural thing to do. One comment about this is that this squared error has no awareness that the numbers are being interpreted as probabilities. We would prefer to have some way of measuring agreement that has awareness of the fact that we're comparing probabilities in some sense. And it turns out that the sort of most natural way, in some sense, the most mathematically natural or beautiful way to compare, to measure how well one probability agrees with another probability is to use something called the cross-entropy loss function. And I'm going to drop this formula on you. This formula is going to look weird at first, so brace yourself for this. This is the formula for the cross-entropy loss function. And this formula is somehow a mathematically natural or beautiful way to compare how well, to measure how well a probability Q agrees with a probability P. So this is the loss function that we're going to use in binary classification. And let's look more closely at this loss function. So here's the formula. let me first of all just try to convince you that that this loss function does what I'm claiming it does. So here I have a graph of this cross entropy loss function, and P is held fixed equal to 0.8. And Q, here we're thinking of this as a function of Q with P held fixed. And the graph that we get looks like this. And you can see as Q gets closer to P, the value, this cross entropy value gets smaller and smaller. And the smallest that the cross entropy value ever gets is when Q is equal to P. So that's good. Moreover, as Q moves away from P, and especially as Q approaches 0, this cross entropy value gets very large. And that means that we start to pay a more severe penalty when Q does not agree with P. And same on this side, if Q is very close to 1, the cross entropy value is very large. So we pay a severe penalty if Q is not close to P. So this cross entropy loss function, at least it does, according to this graph, it does what we want it to do. It measures the agreement, how well Q agrees with P. If the cross entropy value is small, that means Q agrees with P closely. If the cross entropy value is large, that's a bad thing. That means that Q does not agree with P very well. Okay, now I still have not explained where this strange looking formula comes from. And actually, I'm not going to be able to give a fully convincing explanation of that. But what I can tell you is that if you take a course on statistics like Math 371, then you're going to learn a technique called maximum likelihood estimation. And if you use the maximum likelihood estimation technique to estimate the parameters in our prediction function, then this formula pops out. It just pops out. It emerges from the calculation. And that's probably the most straightforward way to discover this strange looking function. There's also other interpretations. Another interpretation of this cross entropy value is, imagine tossing a coin, and it's a biased coin. So the probability of landing heads up is P. But suppose that you mistakenly believe that the probability of landing heads up is Q. So the true probability is P, but you mistakenly believe the probability is Q. And then you could ask, how surprised are you going to be on average when you observe the result of a coin toss? And in some sense, this number is measuring the average surprise that you will feel upon observing the result of that coin toss. I'm not going to give the details of that explanation, but just at least I'll tell you that other explanations like that are out there. Okay, any questions? We've got our prediction function. We've got our loss function. We've learned what the cross entropy is. Cross entropy is a big deal in machine learning. Because why? In machine learning, we're always doing classification problems. And whenever we're doing classification problems, we always use cross entropy, or at least we usually use cross entropy to measure how well our predicted probability agrees with the ground truth. So when you get into machine learning and deep learning, you hear people talk about this cross entropy all the time. Okay, finally, how do we put these pieces together? This is our prediction function. These coefficients, beta 0, beta 1, beta 2, and so on, beta d, these are like knobs that we can tune. And our goal is to tune these knobs in order to make our prediction function as accurate as possible. If we can do a good job of tuning these knobs, then we're going to get a good prediction function. And so our whole challenge is to tune these knobs. we have to find good values for these coefficients. And so how are we going to do that? So what we hope is that for each example in our training data set, we hope the predicted probability agrees closely with the ground truth probability. In other words, we hope that this cross-entropy value is small for each example in our training data set. And another way to say that is that if we compute the average of all these cross-entropy values, where we're averaging over all the examples in our training data set, we hope that this average cross-entropy value is small. And so this gives us a way of choosing the parameters in our prediction function. We need to choose our vector of parameters to make this objective function, capital L, as small as possible. And once again, I have not said how we go about actually finding a vector, a parameter vector that minimizes L. But all I'm going to say for now is that it's kind of like what we do in calculus when we're minimizing a function and we set the derivative equal to 0. And here's a piece of good news for you. There are libraries out there that will do all the hard work for you. So for example, there are libraries that will minimize this objective function for you. And if you're using PyTorch to do deep learning, then you're going to need to minimize this objective function, but basically PyTorch is going to do the hard part for you. Okay, and here's an example. This is going to be, we're almost at the end of this little tutorial. Here's an example of actually doing binary classification in Python. And here we're using this library called scikit-learn, which is a popular machine learning library. And here we have just like 10 lines of code. When you use this library, scikit-learn, you can do binary classification in just like 10 lines of code. And the thing is that scikit-learn does all the hard work for you. Even if you don't understand the math that well, even if you're still working on internalizing the math, you can still use this library without even understanding the math very well. So let's try to look at what's going on in this code. So scikit-learn contains several toy data sets. And in this data set, we're loading a data set. In this data set, each example in the data set is like a tumor. And we have a list of numbers describing each tumor. And the numbers in that list are like the area of the tumor and like the age of the patient. And our job is to classify the tumor as like malignant or non-malignant. So here we're loading the data. This variable X contains all the feature vectors, and this variable Y contains all the labels. Okay. Now in this line, we're splitting the data into a into a training set that contains 80% of the data. So we're going to use 80% of the data to train our prediction function. And then we're going to use the remaining 20% of the data as a test data set, just so that we can test whether or not our prediction function is able to make good predictions on data that it has never seen before. And now here we're actually creating a classifier. This variable CLF, this object is a classifier, and it's a classifier that's going to use logistic regression. And in this line, we're training our model. All the hard work is being done for us in this one line. Remember how I said we have to minimize that objective function, capital L? That's what's happening in this line. Scikit-learn is minimizing that objective function for us. It's tuning those parameters. It's tuning those knobs for us. And then here we're making predictions. And then here we're just computing the accuracy of our predictions. We're counting how many of our predictions agree with the ground truth label. And it turns out that 92% of our predictions agree with the ground truth label. Okay, so we have 92% accuracy. And it just took 10 lines of code in Python. This is an easy way and a fun way to get up and running with doing machine learning. With just 10 lines of code like this, you can like participate in a Kaggle competition. Like you're probably not gonna win. You're not gonna win the Kaggle competition, but you can at least get on the leaderboard. You can make a submission and you can get on the leaderboard. Then you can try to get clever and you can try other methods and stuff. Another thing that we haven't talked about yet is multi-class classification, where we have more than 2 classes. But I'll just leave that as something for you all to ponder. How you can ponder, how would you take these ideas that we talked about for binary classification, and how would you possibly adapt them to do multi-class classification? That's a good question, and that's something to ponder.